All right, let's get started. Welcome everyone. Today we are going to continue talking about imitation learning. And so let's start with a little recap and we'll get into the weeds of imitation. So if you remember from last time, we kind of introduced this framework of the Markov decision process, right? So we said it's a Markov chain augmented with actions and rewards. They're governed by these transition dynamics that tell you how if I feed in a state, in an action, it transitions to the next state. And we introduce a bit of notation saying the Markov property is obeyed, which you've seen lots of times before, right? And the trajectory is a sequence of states, actions, rewards, next states, next actions, rewards that you take when you're sequentially acting in the environment, right? And so one thing to note is if you remember the first module that we had, right? It's actually closer. It's not quite an MDP like what we did in state estimation. So we certainly didn't have the rewards when we did state estimation, right? But we also never observed the states. We like only observed observations, right? And so one thing to remember is that in the MDP setting, so what we're going to do for imitation learning and RL for now is we're going to assume that we can like magically see these guys. And so we're not going to deal with the partially observed setting. There's lots of nice algorithms for the partially observed setting, but they're a little more complicated. So that's going to be our abstraction. So our goal in this setting is to learn a policy. Policy is going to be denoted as pi theta. Right, so pi theta is a stochastic function, which means that it goes from ST to some probability distribution over AT, where let's say it is a Gaussian, right? So like your Gaussian might have your mean as a function of theta and ST, and your covariance as a function of theta and ST, right? So you might think of like, essentially what's happening in your policy is you're mapping from your input state into the parameters of probability distribution. So this could be a Gaussian, it could be a table, it could be a mixture of Gaussian. And more recently, it's been like other generative models. So it's been things like diffusion models and flow models and autoregressive transformers and so on. So your policy could be anything as long as it represents a distribution over actions given state. Right. So you can kind of think of it as like state goes in, does some neural net magic, and outputs some distributions over some parameters. And our goal is to figure out those parameters theta, right? So our goal is to learn these parameters theta. And we're only going to learn it through experience. That means we're only going to learn it by interacting with the world. We are not given the dynamics of the world. Right? We're given access to sampling from the world. We're given access to the reward function. But we are not given access to the dynamics. You can't take gradients back through it. Okay. And the objective we care about is the expected sum of rewards, which is saying that if I drew trajectories under my policy pi theta, I want to maximize the sum of rewards under those trajectories. And so when I say draw trajectories under pi theta, that means you sample an initial state, then you sample an action from pi theta of A naught given S naught, then you run the action in the world to give you S1 from P of S1 given S naught A naught, right? So now I'm at S1 and I sample an A1 from pi theta, and then I repeat, right? And so you can kind of think of this as a sequential sampling problem. You start from S naught, get A naught, you got S1, you got A1, and so on. And so our goal is going to be to try and figure out, like the important thing is that you can see that the states depend on each other. It's like a chain where the states depend on each other. The decision you make at one step affects the next step, affects the next step, affects the next step. Right? And so we're not trying to make greedy decisions. You're not trying to make one-step decision. You're trying to make multi-step decisions. And that's why it's a sequential decision-making problem, because it's not just that you want to maximize reward here. You want to get to the next stage, next stage, maximize the cumulative reward. A variant of this that you'll often see in the literature is with the discount factor, right? So the discount factor is often, instead of just the sum of rewards, you'll have like a gamma to the t, r of STAT, right? Where gamma is a function is a number between 0 and 1, right? And so you can kind of think of it, the discount factor is telling you how urgently do you want to get the reward? How greedy do you want to be? So gamma equal to 1 means you have no urgency. Gamma less than 1, like the smaller the gamma is, the more the like greedy rewards matter, right? And so you can kind of think of this as a way to like encode the bias that you want to get rewards as quickly as possible. And if you're ever in the infinite horizon setting, so when you have an MDP, sometimes you're in the finite horizon setting, which means that you have t steps. Or you could say you're in the infinite horizon setting where t is infinity, right? And so if t is infinity, if you don't have a discount factor, that sum goes to infinity. Right? And so, or it can go to infinity. And so in those cases, you really want the discount factor. I'm going to omit it because it makes the notation a bit cluttery, but you'll often have it. Okay, so that's the recap. What we're going to try and cover today is start off by just quickly recapping behavior cloning. We'll talk about why it's a bad idea. Then we'll talk about compounding error, multimodality. Then I'll tell you why behavior cloning actually works unreasonably well, even though it's a bad idea. Undoing the whole lecture, and then we'll wrap up with some advancements that have been made recently. Okay, so if you remember the setting for imitation learning, right? We are considering a setting where we are given traces of expert behavior, right? So we're going to say we have a data set. The data set has state action pairs, right? So in trajectories from the expert demonstrator, so it says a bunch of states and actions that the expert took, right? So we kind of often denote this as sampled from pi star. Right? So you don't know pi star. All you have is trajectories from pi star, right? So we're going to say like, we're not going to try and be better than the expert. We're just going to try and replicate the expert, right? So in this algorithm, we're going to call it behavior cloning. We're not going to do better than the expert. We're just going to try and replicate the expert. Now, the way we're going to do it is we're going to treat it as a supervised learning problem, right? So you're going to originally what the expert is going to do is the expert is going to like execute entire trajectories in the world, right? Then what you're going to do is take those trajectories, which are actually sequences of states and actions, break them up into chunks of state, action, state, action, state, action, and then try to learn the mapping that replicates going from state to action, right? And so you want to say like, I want to find the parameters that when fed in state produce action with high probability, right? And so our goal is going to be to say, let's take these trajectories, let's break them up into little chunks of state action pairs, let's jumble them all up, and let's treat it like a supervised learning problem. So it's just like saying supervised learning works great for language and for vision. All your, LLMs and all your VLMs and all your vision models, all of them use supervised learning to some extent. More recently RL, but generally supervised learning. So why don't we just do the same thing? Right? And so the way to understand this objective right here, right, is you're trying to maximize the likelihood. So this, you can think of this as the log likelihood of producing the action A star when fed in S star, right? So imagine that you had a Gaussian, right? And let's say this was what A star was, right? What this objective is going to try and do is going to try and move your Gaussian this way. Okay? So just maximum likelihood. So I have the pseudocode in a few slides, but let's see. Do I have it here? Yeah. So really, this is the whole pseudocode for supervised learning. It's trivially easy, right? So we could even go through it, right? So all you're doing is you're like, this is your data loader. You're loading in your data. You're saying you have an action prediction. If it's discrete, you have a categorical model. If it's continuous, you have a Gaussian model. And then you just say, treat it as a supervised learning problem, minimize your loss. Your loss in this case is negative likelihood, negative log likelihood. And then you just repeat, right? So it's super easy code to write, but you're just treating it as supervised learning. Okay. So this is a pretty old idea. And this is first in 1989. I think Schmidl covered this in his lecture a little bit, but this is this work called Alvin from this researcher Pomerleau. And Alvin was trying to drive this car around with these kinds of map inputs and like 30-unit neural net. And it was actually not bad. It was actually not bad for the time, right? It was driving on these roads, and we were doing self-driving with neural nets back in 1989. Pretty cool. But since then, things have really advanced a lot. So here's some examples from 2025, 2024. On the left is the human data that people are collecting. We'll cover this in some more details, but the idea is that you could collect human data that way and then you can have fully autonomous behavior like on the right. Right? So on the right, you have behavior, which is a robot executing cleaning of dishes fully autonomously. The dish is in a slightly different position. The robot's in a slightly different position. You can disturb it and it tends to work. Right? So it's not just like 1 degree of freedom left or right, like you can actually control a high degree of freedom by manual system. And we'll cover a bunch of other cool examples, but arguably imitation learning is amongst the most successful methods for robot manipulation today. Cool. All right. So, if we think about this problem a little more conceptually, right? We'll see that imitation learning has a fundamental error. And so the errors are a fundamental issue. And the issue is what we call compounding error. Right? So can someone help me think through any guesses on what the issue of compounding error is? So remember what we did is we took these trajectories, which is in a sequential decision-making problem, and we chopped it up into individual pieces, and we just said, at this state, predict this action, at this state, predict this action. We treat it as a non-sequential problem. Right? And so what could happen if we do that? What could go wrong? Any guesses? What happens if you take a non-sequential problem or a sequential problem and treat it like a non-sequential problem? You can deviate really quickly. That's it. Right? So, but it's a little more nuanced than that, right? So this figure kind of shows it to us, but essentially what happens is, imagine this was your optimal trajectory. Okay. Now you're going to do supervised learning, but even if your supervised learning was really good, right? What's going to happen is you'll make tiny little mistakes. The mistakes could be really, really small, and if they're evaluated, all separately, they will be fine, right? But the important thing is what happens when they're like evaluated in sequence. So imagine I made a tiny little mistake here, right? And if it was one step, I'd be fine, right? But what's happened now is I'm at my first step. I've made a tiny little mistake. Now I'm at this new state, S prime. But S prime is not what the training distribution was. S prime is different from the training distribution. It's out of distribution, right? And so now I'm querying the state on something that's a little bit out of distribution. And so it's going to make a bigger mistake. Now I'm querying it on something that's out of distribution. So it's going to make an even bigger mistake, right? And so what leads to the deviation is that when you apply things sequentially, you start querying the learned policy, right, on states that it's never seen during training. And so the important thing is during training, I've only seen this guy. But during execution, I start seeing this, which I've never seen before. Right? And so nothing during training told me what to do in those states, and so you quickly deviate. And so you can call this covariant shift. You can call this compounding error. All of those are the right terms. But when you look at this kind of mathematically, right? So the important thing is this is your training objective, which says that I'm going to take states and actions from the expert distribution. But when you execute it under the policy. Right? So the important thing is the training objective was under the expert policy, but the evaluation objective is under the learned policy. And those are not the same. Right? And so the important thing is the states that you visit when you act sequentially are not the states that you trained on. And so unless I like magically cover those states, for instance, like I'm not gonna know what to do. And if I don't know what to do, I'll keep making bigger and bigger mistakes. And so the fundamental way of thinking about this is that the training and test, like in machine learning, training and test should always be the same. And if training and test are drawn from the same distribution, you're happy. But what's happened here is that training and test are not from the same distribution. Training is from the expert and test is from the policy. And that's going to lead to a lot of trouble. And so this happens in practice too. This is again an example from Alvin. You'll see that it like drifts off the road and leads to all sorts of trouble. And that's why we didn't have self-driving cars in the mid-90s. Okay, so conceptually, think of it as anytime you make a mistake in a sequential decision-making problem, you'll go more and more and more and more out of distribution. And our goal is going to be to figure out how to deal with this problem. Right? Okay, so question is, if I am going out of distribution this quickly, is all hope lost, or can we fix this problem, right? And before I give you the answer, how do you guys think we should deal with compounding error? Simple, right? You make a little mistake, you don't know how to recover. So how do we deal with compounding error? Ideas? Yeah. You could do some PID. The answer is going to look a lot like PID. Um, the tricky part of the imitation learning is that you're not necessarily told what the target should be. So like in PID, you like know what the target is, and you're trying to go back towards it. But in imitation learning, you're just trying to produce an action. So you don't necessarily know what the like on this path that we had, right? Like let's see if deviated. Like what you're trying to get at is like, let's go back there, right? But I don't know what the target is. Like I don't know what this state actually is, right? Because I'm going to deploy the policy in a brand new scenario. And I don't actually, it's not a trajectory tracking setting. It's just like I'm going to run my policy. No one tells me what the next state should be. So, but if we did know that, that would be a good idea. Yeah. But our solution is going to look a lot like that. Okay, so let's try to get into some of these solutions. But maybe the first thing we should look at is a solution that some folks had from NVIDIA back in 2016. And so they started like trying to apply imitation learning and behavior cloning to self-driving. This in Santa Clara, right? And so they were driving their self-driving car around. I was doing all sorts of crazy shit. Right, is clearly running into stuff or swerving. I don't know. A bunch of behavior that looks a lot like behavior cloning messing up. And so okay, so they were like, okay, this is Jensen's going to be extremely mad if we deploy this on the streets. And so they came up with a really, really clever solution, which led to a lot better. This is not those words, that's like concept. No, he doesn't doing that. Looks a lot better than it did earlier. Okay, and the solution that they did was actually like feels like a little bit of a hack, but I think it's super clever, which is that instead of having one camera facing straight, they had three cameras, one that faces straight, one that faces a little to the left, and one that faces a little to the right. Okay, and so what they said is normally what you do in behavior cloning is you record the middle camera and whatever actions you take. But what they're going to do is they're going to record the left camera and the right camera. And they're going to say, okay, for the middle camera, you keep the actions the same. But for the left camera, your actions are going to be to go to the right. And for the right camera, your actions are going to be to go to the left, right? So it's basically saying that if my car had been facing the way that the left camera had been facing, that means you're going to like go off the road to the left. And so you need to correct yourself and come back to the right. And if you're going to go off the road to the right, you need to correct yourself and come back to the left. So it's a little bit like PID in a way, right? In the sense that this is your trajectory. And what they're saying is, okay, like the front camera is what it is. But if your car had not been facing this way, but actually had been facing this way, then you should have taken this action. If your car had been facing this way, you should have taken this action. Right. And so what they're actually telling you to do is like telling you how to recover from any mistakes that your policy might have. So if your policy is starting to drift, like it tells you to fix it. Right. And the cool thing is that they did this without having to collect extra data in the world. Right. And so the reason it's so clever is because it's a trick that is able to just take normal driving data and just with two extra cameras give you corrective behavior. And more recently, people have applied these things in other domains, but until 2025, like this only worked on driving. Like it doesn't, how do I do that for manipulation? I don't know how to do that for like a robot arm because there's no left and right and stuff as easily. But there's a general principle that's useful here, which is saying that if I'm going to keep making these kind of compounding errors, I'm going to keep deviating off my optimal path. What I want to do is I want to figure out how to go back from I want to figure out how to recover. And I want to figure out how to go back from my deviated stuff to my good stuff, right? And so the general principle that we're going to kind of take on is we're going to try and get labels that take us back from suboptimal data to the optimal data. So you're going to get kind of corrective labels that correct for this kind of drift. So we're going to think of different ways to get these corrective labels, but essentially the top figure here is showing compounding error. Like the dotted line is where you wanted to go. The solid line is where you actually went. And what we want to get is corrective labels that bring you back, kind of like PID, right? But it's the learning version of PID. So we want to figure out how to get these labels that if I was in X2 hat, I would go back to X3. If I was in X1 hat, I would go back to X2, etc. Does it make sense? So it's saying that like, it's not saying that I'm not going to have the fuck up. It's like, I will have the fuck up. I will get off the path. But if I do, then I don't go too far off the path. I keep coming back. Right? So it's reducing like like you can kind of think of this as like a tightrope. You're on this tightrope, right? And earlier what would happen is if you fall off the tightrope, you plummet to your death. And so it's all bad. But what we're going to say now is if you fall off the tightrope a little bit, you know how to correct. You fall off the tightrope a little bit, you know how to correct. Right? And so you're going to like keep staying on the optimal path because you continue to have corrective data. Questions? Does that make sense? Are there any pitfalls with this? Like it's like an intuitive idea. Yeah.
I guess it feels like it just kind of widens the scope of like the allowable error.
Yeah.
But if you get too far off that, then that's
Exactly. So it's not a silver bullet, but at least it helps you deal with the errors that come from your own sequential mistakes until some point. Okay. The other pitfall is if I needed to get this kind of corrective data, I might have to go experience it. And that's like potentially a big problem. But let's see how people kind of thought about this, right? So if you think about the difference, right? Your training data, let's call it P data. And the data that you visit under your learn policy is P pi theta. The fundamental issue is coming from the fact that P pi theta is not the same as P data. Right? So the things that you visit under your learned policy are not the same as the things that you visit in your expert policy, right? And so there's this like fundamental train test mismatch, which is causing our problems. And so some folks at CMU, a lot of collaborators of SIDS actually, we're thinking about, okay, can we do something simple to make P data and P pi theta the same? And we want to minimize the train and test shift. And so they did this, the simplest possible thing, right? So the fundamental thing they thought about is, can we try and make the training data, P data, similar to the things that you saw when your policy was rolling out? And so you want to make the training data of your policy the same as the things that you got when you're rolling out. How might we do that? So this is like training, and this is like test. Oh no. Oh, see something things. Good. Okay. So we want to make P data equal to P pi theta. How might we do that? Any ideas?
just create data from
That's it. Right. So the idea was really simple. It's just saying that like essentially run your policy and get more data on the states where your policy messed up. Right. So just saying that you want to make P data or P training equal to P test. Well, just like keep adding all the places where you messed up to your training data. Right. So it's kind of like playing whack-a-mole. Right. So one way to think about it is, let's say this was your expert data. Okay. You learned something. And let's say your policy kind of goofed up. So what we're going to do is we're going to do an iterative process where you're going to say, okay, on these states where the policy messed up, query a human, and the human is going to provide you what they would have done in those states, right? And so let's say it messed up two different ways. You're going to ask the human to provide you what they would have done in those states. Then you add them to the training data, and then you retrain and you repeat, right? And so essentially there's an algorithm called dataset aggregation, DAGR. And what Dagger does is saying that like every time you train your policy, you run it, you get the states that it visited, the messed up states that it visited, ask what an expert would have done in those states, add that to your training data set and repeat, right? And so essentially what you're doing is you're saying, okay, well, I'm accepting that I'm going to make a mistake. I'm just adding all of those mistakes into the training data, right? So if I wanted, for instance, this kind of like corrective data on the bottom, right? You can think of it as like, well, I ran my policy to see where the mess ups were. Then I asked a human to fix those mistakes for me. Then I added all those fixes back into the training data. That's it. So almost a silly, it's almost like a silly, obvious algorithm, but it wasn't silly in 2011, right? So let's kind of run through the algorithm mechanistically, right? And so we're going to start by collecting some training data, normal expert imitation learning, collect some training data. You're then going to train your policy using maximum likelihood, supervised learning. But the important thing is then you're going to run your policy in the world, right? So you're going to run your policy in the world. It's going to give you the observations that it visits, like it's going to mess up. It's going to get to some things where it's messed up. On those mess ups, you're going to ask the human to label them with optimal actions. So let's say you ran your policy, you got O1, A1, O2, A2 till ON, AN, right? What I'm going to do is I'm going to throw away the actions that the robot took and replace them with actions that an expert would have taken. Right? Pi star O2, pi star ON. So I'm going to replace all of these actions that were wrong with the actions that were right from a human. I'm going to add those back into my data set. I'm going to repeat. Yeah. So it's almost like um, a stupidly simple algorithm, but you can show that it converges and you can show that it like deals with the compounding error issue. And yeah, so good. Data needed to like converge with common policy, or is that really your problem? There are a bunch of bounds on there are a bunch of bounds on how much data you need, and it is like what you can show is that the amount of data you need is going to be smaller if you collect it this way than if you just try to cover the space uniformly. Right? So the important thing with Dagger is that, okay, if I wanted to just add more data in, like one of the tricky things is, okay, I'm querying my person to add more data in. I'm not just adding data anywhere. So like imagine that this was my expert. I could just say I need more expert data. So I will collect more data and more data and more data and more data. And I have like some uniform likelihood of sampling stuff around here. But what Dagger does is it samples just the data that you need, right? And so like the amount of data that you need is exponentially smaller than if you just collected more data, right? So the important way to think about Dagger is, yes, you're collecting more data, but you're collecting more data in the regions that are important to fix your compounding error, not just everywhere. And so if you were to, like, maybe one way to think about it is, if I had a limited budget of data and I wanted to collect data, like this is the right data to collect because it's fixing the mistakes that you had. Whereas if I just collected more and more data, I'd still have more and more mistakes, perhaps. Like pre-training data set that you use for like the initial is good enough, right? It's really not like, let's say just like yeah. And then you can. So we're gonna assume that our pre-training data sets from a near expert policy, and we're gonna assume that the supervised learning procedure has some epsilon error, and so all the error of Dagger is gonna scale with epsilon. Okay, so yeah, the important thing to remember Daggers, it's better than just adding more data. Go ahead.
Could you like clarify the first line?
This one?
No, just like
Oh, this one? So when I say P data, that is like, what is the distribution of training data observations? So this is like whatever your policy is trained on, right? So like the procedure is going to be, there's going to be some data set. That data set is going to go into supervised learning. It's going to give me a policy pipe here, right? And so this is what happens. This is the coverage of observations in my expert data set. This is what happens when I run my policy. So this is like the set of states that I visit when I run my policy in the world, right? And so P pi theta is what happens when I run my policy. P data is what did I train on, right? So Okay, so simple procedure. It kind of works, right? So here's an example from some folks at CMU where they showed that you can get like a drone to like fly around a dense forest, just using this dagger type algorithm, and fly for significantly longer than we could before. It's not perfect, right? But maybe let's go back to this algorithm and let's see which things about it are not perfect. Like, what are the problems with it? Yes,
Takes a lot of, I guess.
it might take a lot of training. So one of the issues is ask human, right? So you're asking human all the time. And the other thing that's kind of awkward about Dagger is that you're asking people to label things at the observations that the policy visited. So like it's like imagine this was your expert, you like let the policy run, then you go after the fact and say, hey human, if you were here, what would you have done? Or if you were here, what would you have done? Which is kind of like an awkward question to ask a person. So it's both asking the human and you're asking it to label it after the fact. And so there's newer variants of Dagger where people just take over. Like let's say you're messing up, you can just like take over and correct. But the original version of Dagger is not taking over, it's labeling after the fact. It's a little awkward. Like the way to do it is you'd show like pictures of the drone where the drone was, and you say, what would you have done in those situations? Which is kind of awkward because you like usually like feel out how to do things, not just like label them after the fact. What else is the problem here? Just looking, it's just in these 4 lines. Yeah.
If you have label one state, then if it like affects the action, then the rules go to the other ends. Right? So the other labels will just don't have those.
It'll get wasted. Yeah, that's a good point. So you're essentially saying, okay, like if I gave you this label, then like why would it ever come to any of these states? And so am I wasting my labels? Right. So there's a nice line of work on like active preference labeling. So like or active dagger, so you can like choose which states to do labeling on. Another issue here is that you have to run your policy, right? Like you have to actually execute your policy in the world. And so I have to run my policy in the world. And as we said before, it's like if that's a car, that means I have to let the car run until it messes up, right? Or I have to let my drone run until it crashes into a tree.
The thing I thought of here, were, like, I guess like Tesla, like how much data they manage to collect.
Right.
And how that must have created a big gap, type of like algorithm.
Right. But if you look at like their stuff now, like often, or if you look at Waymo more so than Tesla, perhaps, like a lot of it is with safety drivers, or a lot of it was until it wasn't. But basically, they would run things with safety drivers to keep providing corrections on the fly. So they like had to deploy their models and collect on policy data to bridge the gap from just purely offline. Okay. So we're going to try and deal with at least these 2 problems. And there's lots of others. It's a whole rich field of study. Yeah. Yeah, we'll cover that next. Yeah, it's the problem raised was what if you have different people who maybe suggest different things, right? So a canonical example of this is imagine that you were in front of like an obstacle, right? And some people go left and some people go right. Like, will I just go through the middle? You know? And it's a real failure, right? And there's like solutions around it, but it's not true. So good question. Okay, so we're going to start by fixing Dagger. And the 2 things we're going to try and fix is, having the human generate these corrective labels and like that being kind of tedious. And then having to run the policy online and having to like experience the failures during the training process, right? So we're going to try and fix those 2 with some new algorithms. So maybe let's think about the first one, which is I want to avoid running my policy. I want to avoid running my policy in the loop, right? And so I want to kind of get these corrective labels, but I want to avoid having to like train my policy and run it and train my policy and run it and train my policy and run it. So how could I avoid doing that? I guess I gave you it. But the answer is by like doing it at data collection time, right? Which is the algorithm called DART from some folks at Berkeley. But the algorithm is super easy. It's just saying that when you're collecting data, don't collect data on a clean trajectory. Try to inject some noise during training, right? So what that means is that what a clean trajectory would do, it says like let's say this is where you started. Let's say this is where you wanted to go. Right? Like a clean trajectory would be like extremely narrow, right? So it's like your tightrope is really narrow. If you fall off it, you're screwed. And so what you're going to do instead is most data collection is done by teleoperation. So someone's going to control a robot interface. And so let's say when you're doing teleoperation, you're just going to inject a little bit of noise into your training process. So let's say the human commanded this, you are going to instead command this. If the human commanded this, you're going to instead command this. And so you're going to inject a little bit of noise into the training procedure. And then you're going to have the human essentially correct for that noise. And so the key idea is that rather than having this in the loop training, run, training, run, training, run, you're just going to have the human collect a broader set of data at training time. And so you're going to inject a bit of noise into the training process. And then the human acts like a corrective label at training time because they have to collect for the noise that was introduced, right? And so you can kind of think of this from the perspective of maximizing likelihood, but you want to do it while there's noise injected into the data collection interface, right? So the one way to think about it is you're like trying to pick something up and imagine something was like a little noisy when you're trying to pick it up. And if you want to get it to behave, you have to correct for it. Yep. A little bit unsafe. Yeah. And then the art to this particular paper is that they talk about how unstable what is the minimum amount of instability you need to introduce in order to get it to behave well under compounding error. So if it's too unstable, your like interface is doing something crazy. But if you inject a little bit of noise, then you tend to recover nicely. Right? But the nice thing is that I didn't have to do this train, run procedure. I just collected a tube around this optimal data at training time. So you can there's a bunch of other nice work if you're interested on tube MPC and tube imitation learning. But the idea is that if this was your optimal trajectory, you just have the person collect data in a tube around it, but the tube kind of like brings you back. And so you're still having a human provide the corrective data. You're just doing it at training time or data collection time. Make sense? So if you're ever doing imitation learning, just add a little bit of noise into the training interface. It'll like massively boost your performance. There's also another reason if you ever do imitation learning in simulation, if you guys are interested, when you train things from a reinforcement learning policy, it's often a lot easier than if you're training things from like a human, because humans will often do things kind of cleanly compared to reinforcement learning policy, which is like trained with noise. So it is like often like already giving you the tube. So, okay. The issue is if I'm trying to do something like robotic surgery, I certainly don't want to add noise to my training set, right? And so I don't want to be, suturing someone up and just like wiggling my arm. And that is it's a liability for sure. So, so the next question that this is actually from some of my students, we asked, how do we get this kind of corrective behavior without requiring this noise injection at training time? And so what they tried to do is they tried to ask the question of, can we generate corrective labels automatically? Right? So can we kind of get this behavior where we go back to the optimal data without having to run it in the real world, without having to inject noise during data collection? Okay. So the question is, I want to obtain these corrective labels which bring me back, like stop me from drifting too far, but I want to do it without experiencing failures in the world or burdening the human, right? And so the key object that we're going to use for that is we're going to use this idea of a dynamics model, right? So the idea of a dynamics model, same thing as a world model, right? It's just saying that it's something that takes in your state, in your action, and predicts your next state. And so what we're going to try and do is we're going to try and use a world model in order to figure out how to go back to the optimal data. Right? And so the high level idea that we thought about here was if we knew the dynamics model of the word F, right? Then if you wanted corrective labels, you just need to find the states and actions that bring you back to optimal states in the training data set. Right? And so you can try to solve this optimization problem to say, let me just, given an F, find an S and A that bring me back to an optimal state with high likelihood, right? So it's kind of saying, imagine you had an optimal trajectory. Let me search for S's and A's that bring me back to the optimal trajectory. If I knew F, right? So the F tells me how the world works, and I'm going to use how the world works to say how to come back. Now, what's the problem with this?
Would you like assume that your dynamics model has to be pretty?
Your dynamics model has to be pretty good, right? And so the tricky part is you don't know F, right? So you want to get like you shifted the burden from the human into F. Oh, I don't know F. If I knew F, would that be done, right? And so what we're going to do is we're going to try and learn F, right? If we're in a learning setting, we're going to use our big neural net hammer to try and learn F. And so we're going to take the states and actions that we collected, and we're going to use them to train an F, right? So we're going to go from F to, we don't have F, but we're going to have some F hat, right? And F hat is our approximation to our world model, but we're only going to train it on the data that we collected. And then we're going to do the same thing. We're going to try and find states and actions that bring me back to the optimal states. But the important thing is we trained F, like F was only trained on expert data. Right? And so what's the problem with F was only trained on expert data? What happens with this problem? What are some issues?
Not with the models there, so it's not really person.
That's right. So your F is only limited coverage. And if your F has limited coverage and you solve that optimization problem, it'll find all the holes in your F. Right? So it's going to like say, F is going to maybe be okay in some region around here. But if I run this thing without any constraints, it's going to like predict that this thing can teleport to here and this thing can teleport to here. It can do whatever it wants, right? Neural nets are terrible at extrapolation, at least at this scale. And so the intuition that we're going to do is we're going to just constrain this search to only be in the regions where the model can be trusted. And so instead of saying that we're going to try and get corrective labels from an F anywhere, we're only going to get corrective labels where the model can be trusted, right? And so if we have a model F phi hat, instead of collecting data everywhere, we're just going to collect data in a small tube around the optimal data. And we're going to impose a small extra constraint on the model that it has to be smooth. So if the model is smooth, then you can trust it in some region around the optimal, and you can synthesize data that comes back. And so I'm going to skip a lot of the details here, but if you can show that your model F phi hat was reasonably smooth, then you can show that if I constrain my search to only be in the regions where the model can be trusted, then you won't generate like magic hallucinations like going from here to here or here to here or here to here. You'll be in the things that are reasonable. And the cool thing is, what my students showed is that with this kind of approach, you can do like fun and extremely useful for practical setting things like putting a coin in a piggy bank with chopsticks. And so we all know this is a task that one should be doing in life. But I think it's kind of fun. I think it's kind of fun as a problem. But if you do it with corrective labels, you're able to do it successfully. And without corrective labels for these really high precision problems, you tend to like have small amounts of drift. So you can see that you end up missing by a little bit and fail. And so the nice thing is here, we didn't collect any extra data. We didn't burden the human with anything else. Like you just trained a model with a few small constraints on the model, and you're able to generate corrective data that brings you back. You can also apply this to like other fun tasks like Lego insertion and grabbing other stuff with chopsticks. My students wanted to grab flies out of thin air with chopsticks. That was not allowed. But yeah, so that's how we're going to deal with compounding error. There's lots of other fun ways to deal with compounding error. So if you all are interested, we had a faculty candidate this last week, Gokul Swami, who had a nice talk on dealing with compounding error and imitation learning. Please go take a look at it. It's on the Allen School website. But we only have 3 minutes left. So maybe let me give you guys some fun videos before we end, and then we can cover the other stuff on Monday. So here's some fun videos of imitation learning in action. So this is some stuff from 1X. It was actually a few years ago. It's gotten better since then. But this is fully end-to-end imitation learning. So they just collected lots and lots of data with the teleoperator, and then they're running this fully autonomously, which is pretty cool. So they incorporated some of these tricks of like adding in a bit of noise and those kinds of things, but really what they did is some version of the behavior coding. And now you can buy some of these for pre-order for your home. Here's one that came out of an academic lab with this platform called Aloha. And they're trying to like cook shrimp here, but this is fully autonomous. And they're able to get this with like a super janky $15,000 robot platform at Stanford. The cool thing about this particular platform is how they collected the data. So they had like this puppeting system where you like have a human drive around and puppet the robot to do stuff in the real environment.
Is limited to rel.
Let me skip this one. This is an example I really like from a generalist. And generalists in the startup that can be like really, I think all of this is just really large scale imitation learning. So they collected like 100,000 hours of data, I think, or some very large amount of data. Maybe anything, see anything. Sort that in this. With Lego blocks and boxes and with large tools. The imitation learning works well. It can work really, really well. But like they collected shit ton of data with a lot of money. So, more how to get there next time. Yeah, that's all for today. Thanks, folks.